Alright, in this video I'm going to be telling you about the shell method for finding volumes. And this one is not included in AP Calculus anymore, but like a number of other things I want to show you in this class, it is something that maybe a University Cal 1 class would expect you to know. Okay? So really this is a technique that I think is best to look at, out of necessity, right? We've got this region defined by, it's trapped between a downward facing parabola and the x-axis, and we want to rotate that thing around the y-axis. As of this point, you don't have a technique to deal with that, specifically because of the fact that if we're going around the y-axis, we can't exactly do washers because we don't have a formula for this distance in terms of y. Now, I think if you really tried hard and you used the symmetry of this thing, that you could do that. But if we ended up with a function, just for sake of example, that went like that, good luck finding yourself an expression that doesn't have that same symmetry that that one does. There's no way we can use washers with that thing to revolve it around the y-axis. That's just not going to happen. So we need to build a new technique because our shell technique could have dealt with that, okay, if we were rotating around the vertical axis. So the thought is if we rotate this thing, and I'm not going to really be able to draw it. I think it's going to, I don't really know what it's going to look like, but if we were to rotate it, let's see, maybe I'll kind of draw it the way that I told y'all to draw your diagrams when we were working the disk and washer problems. Okay, it would be to start off with the region we're going to be rotating. That wasn't a very good drawing. I can do better than that. Start with the axis of rotation. And then what I'll do is we'll draw that. That might be better. And then I'll draw the bottom of the region. Okay. So what we need to do is we're going to rotate this thing around the y-axis. And, as the name indicates, we're going to be looking at shells of volume. So what's going to happen is we're going to track the movement of this piece right here as it rotates around the y-axis. All right, so what I might do, this is kind of risky, but yeah, I kind of drew it in softer there. Well, I'm going to have this kind of mirrored image there. And this is going to make like a band, right? I'm a little scared to draw it on the board for you because I didn't draw it that big in the first place, but that's about what's going to happen, and then that'll be the front of it. Okay, there will also be a back, obviously, because we're going to be rotating this thing around the y-axis. All right, and that's one of my shells. Okay, and it's if I were to cut it out, it would have barely any thickness at all. Okay, so I think what I need to do is I need to kind of take this thing, bring it down here, lay it out. And then say, and I guess we need to also talk about the, we're going to add a bunch of these up. So we're going to need to also talk about the lateral area of a cylinder. Okay? So I think I'll do that right now, then I'll come on back. Okay, so say you've got yourself a cylinder. The area there, well, if I bring it out here, this is 2 pi r, and that's L, where L is going to be, I guess, the height of my cylinder. Yeah. And R is the radius of the circle that kind of dictates that. Yeah. Okay, so that means that this is going to be 2 pi r, and that's going to be L, right? To use the same kind of terminology there. And then we're going to need to determine what are R and L in terms of X or Y or whatever. Well, L, being this height, is pretty clearly equal to f of x, right? L is going to be 2x minus x squared. And then 2 pi r. Well, what is r? R is the distance from the y-axis here, or the y-axis to here. That's just x. Okay? since we're rotating around the y-axis. Suppose we were rotating around a different vertical line, we would have a, some sort of other expression for r. It wouldn't just be x, but for now I'm going to just say r is equal to x. But we also know that this has got a little bit of thickness to it too, right? This is like a sheet of paper or something. It's got some sort of like, minuscule thickness. So I'm going to call delta something, right? And so if we were to think about it, where did this originally come from? Well, it came from one of these. And if we're looking straight on, that's kind of that's the thickness. And so I'm going to say that the thickness of this is delta x. So my volume is going to start, I always like to start with the idea of the Riemann sum, is it's going to be the sum of the volumes of a bunch of these like sheets of paper, these shells. So the volume of this is 2 pi RL times h, so that would be, wait, hold on, what am I doing? 2 pi x times 2x minus x squared times delta x for the thickness. And then, as the number of shells goes to infinity and their relative thicknesses go to 0, this will become an integral. As x runs from 0 up to, okay, that intercept is going to be 2, of this thing, 2 pi x times 2x minus x squared dx. Okay, first thing I'm going to want to do is factor out a 2 pi. And then I will distribute in the x, so that's 2x squared minus x to the third. And then this is something that we're going to be able to do, without too much difficulty, right? We'll be able to say, okay, 2/3 x to the third. So 2/3 of 8 minus 1/4 of 2 to the 4th is 16. When I plug in 0 into those antiderivatives, I'm going to get 0 back, and so that's going to be my volume. Let's see if there's just another one, or if I want to just kind of give you the formula in general. Let's see. All right, yeah, I think I've decided I'm just going to give you a couple more examples, like reasons why we would want to use the shell method. I'll show you the setup, and then hopefully, because I looked at the general formula, and I don't think it's terribly enlightening. Much like, just giving you a general formula for the washer and disk method is not terribly useful without a bunch of examples to go with them. So here I've got y equals x squared plus 1. And we're going to rotate this, this region G around the line x equals 2. Okay, this is bounded not only by x squared plus 1, but by the coordinate axes and the vertical line x equals 1. So this is one that we actually could have solved before using the washer technique, but notice how, if this is my axis of rotation, that I would need to split it up into 2 separate integrals because, here I've got one kind of radius and a second kind of radius, but over here I've got, it's constant. I've got something different going on. I don't have this x squared plus 1 curve contributing anything. So I need 2 different integrals, and that would be annoying, right? Wouldn't it be nice if we could just write one integral to get our volume here? And we can using the shell technique. So what I'm going to do is I'm going to say, all right, so when I rotate this, it's going to make, a bunch of cylinders, if I was to, kind of slice it out from the middle. And the radius, so I've got, some kind of height. It's 2 pi RL. It's always volume and the weird thing about this one, as opposed to what we're used to, if we're rotating around a vertical axis with shells, it's going to be dx, because the shells are going to kind of like move along the x-axis. So in this case, it's going to be dx as x runs from 0 to 1. All right, so now we need to get an expression for r and l. Well, this is r right here. And much like before, we can do right minus left, top minus bottom. Okay, so I'm going to say that over here, r is equal to right minus left. That is x equals 2 minus x equals, well, whatever x is. So r equals 2 minus x. Yeah, because over here, r would equal 2, 2 minus 0. Over here, r would equal 1, 2 minus 1. Okay. And then L, it's kind of like the height right here, and it's going to be f of x. L is going to equal x squared plus 1. So I'm pretty much ready to go, you know? I'm going to say that this is equal to 2 pi times the integral from 0 to 1 of r times L. It's x squared plus 1 times 2 minus x. I might actually do this right here. It's going to be negative x to the third plus 2x squared. Hold on, 2x minus x plus 2. I can go and do that over here. Right? Let's see, I can do this. How much time? Yeah, still got plenty of time. So 1/4, oh, because it's 0 to 1, and this is polynomial, this is going to be negative 1/4 plus 2/3 minus 1/2 plus 2 multiplied by 2 pi. Okay, and that's a suitable volume. All right, I've got one more example. It's also going to be rotating around a vertical axis. I really am going to trust that if you needed to rotate around a horizontal axis, you would be able to do that. You know, it's just going to be kind of the opposite of this. Your integral is going to depend on y. Your r and your L are going to have to depend on y, and well, you'll figure it out. So, okay, what's going on here? Oh, I know what we should do for the next one. Yeah, I'm going to erase this and put up a new example. All right, yeah, I like this one for a couple of reasons. So what we're going to do, we're going to, again, rotate around the vertical axis. I thought I'd switched it to the vertical line x equals 1. All right, now the reason I like this one is I've kind of added in a couple of things. First of all, this thing's got a lower bound, so our L is going to have to be the difference of two things. And also, if you look at y equals x to the third plus x plus 1, and we were going to rotate this region around the vertical line x equals 1, that feels like a disk situation, right? But that would require us to solve for the inverse function for this thing. And we can't solve for x in terms of y on this expression. Just, that makes sense. Actually, I feel like it should, because there is a cubic formula, right? It might just be really, really unpleasant, or it might just be something that we can't solve, you know, outside of using the cubic formula. But this was an example that the book gave me. What does it say? Oh, it says you cannot easily solve for x in terms of y. I was gonna say, like, it is definitely possible, but we don't want to do it. So, and we're looking for like a way to quickly get this volume and not go, you know, without the cubic formula. Like, nobody wants to do that. We're not going to. So what I'll do is I need to kind of reproduce my region here. All right, and so the shells are going to have height given by, I guess that's L. So in this case, L is kind of like the height. It's the thing that's parallel to the axis of rotation. It's like the lateral. Yeah, it's going to be top minus bottom. So that's going to be x to the third plus x plus 1 minus the bottom, so that's y equals 1. Okay, which is just going to be x to the third plus x. And then the radius r is going to equal, well, it's right minus left, it's 1 minus x. So I know that, you know, where I'm headed, I need volume equaling 2 pi times the integral from 0 to 1 of RL dx. Okay, So RL is going to be, okay, I don't want to make an error here. So RL is 1 minus x times x to the 3 plus x. Okay, so when I run 1 through it, I'll get x to the 3 plus x minus x to the 4 minus x to the 2. All right. So negative x to the 4 plus x to the 3 minus x to the 2 plus x to the 1 dx. Okay, I'm going to just really quickly work that, and there you go. All right, so this is volume with the shell method. This is not particularly difficult or anything too much more than what we've already done in this class, but it is something that finite amount of time in the year, and needing to prepare you for that AP exam, and knowing that this is not on it, it just wasn't really worth our time throughout the year. So hopefully you found this informative. If you did, maybe you should like the video.